Hello guys, this is Sir DB again. So it's a continuation of your uh, analysis of structural fasteners. Okay, so we proceed with our design of slip critical connection. Slip critical connection are actually friction type connections, but this is a more advanced consideration. Uh, Not only giving emphasis to the friction as your uh, main resisting consideration, main resistance for consideration. It also involves the effect of tension uh, and the shear interactions, which will be later uh, discussed and demonstrated in the form of a problem on bearing type connections. So this is normally used when the joints are subjected to reversing fatigue loads. Okay, so when you say reversing and fatigue loads, these are loads coming from oscillating equipments, machineries, vehicular loads. Okay, earthquake, not too much because earthquake is a transient load, but it can be considered as well. So it's also normally used for joints that use oversized or slotted holes parallel to the applied load. Uh, so when you consider slotted holes in which your load is directly parallel to the oversizing or ovalization of your bolt holes, this can be considered. So also for joints in which slip would mean detrimental to the performance of the structure or maybe the non-structural components when the connections are carrying components which are likely to be damaged by the movement or the slip of the members involved in the connection. So the coefficient of friction is normally termed as a slip coefficient ranging from a value of 0.2 to 0.6 depending on the condition of the surface. Example, the Needle scale, oil, paint, surface treatment, etc. Okay, so as a general approach, we may use the shear resistance in lieu of frictional parameters by dividing the frictional force with a bolt cross-sectional area. So instead of using or instead of considering the frictional parameters, we normally convert it into a shear parameter by simply dividing the force mu times T with the bolt sectional area. Okay, so if you divide this, so this is a simple shear uh, this is a simple shear condition. So an example, we determine the force P required to cause slip of a 7/8" diameter, 8325 bolt loaded as shown in the figure. So if the slip coefficient is 0.33, which is the usual value used for a typical uh, uh, section with a clean mill scale surface condition. So using the pretension load from table 4.4.1, so this is the table that I introduced to you in the earlier videos, wherein our bolt tension for a 7/8 inch diameter is 39 kips. Okay, so we simply multiply the coefficient of friction mu k with that of the minimum bolt tension based on the strength of the bolt and also the proof load test. So we get mu k times t, we get the 12.9. So this is not a T, but this is actually the frictional force. Okay, and this can be converted by simply dividing this to the area of the bolt, converted now to a shear resistance. So instead of talking about frictional resistance, we may convert the nature of the the nature of behavior in terms of shear behavior. So since the overall action of the connection is a shearing effect, then the shear stress FB induced in the bolt by the load causing the slip to begin is simply again divided by this AB here. So we get now your shear stress to be equivalent to 21.45 KSI. And this is a simple ASD computation for your shear stress. So note that regardless of the design limit state used, the intent is to prevent the limit state to occur at service loads. So slip critical connections are actually service load conditions, but they can be represented by analytical solutions in the form of inelastic analysis. So connections with oversized holes or slotted holes parallel to the load are required to be designed to prevent slip at the required strength level. In such cases, slip will lead to a significant increase in the load on the bolts. So the reliability index value of 4, which actually defines your factor of safety, is used for the slip critical connection, which is higher than that used for the welded and the bearing type connection, because the latter fails in sudden non-ductile fashion. For these reasons, the bearing the shear strength slip critical connection must always be evaluated. Okay, so if you want to make use of reliability analysis, this is the index used for your factor of safety, the margin of safety in consideration of your slip critical design. So the factors affecting slip critical connections are, of course, the frictional coefficient, the pretensioning method, the method used, and of course the size of the hole, because if the holes are oversized, then slip critical connections more is much more to be considered in terms of serviceability conditions. So for the design of the slip critical connection in LRFD, we refer to the AISCJ 3.8 definition of the slip limit state nominal resistance in the form of mu DUHSC and STB, where these are all parameters, and we take note that the TB here simply is the um, the main dimension upon which your force Rn or your nominal resistance Rn is uh, computed. So all of these are parameters or factors considered. Mu is the coefficient of friction for the different classes of surface condition. D is the ratio between the mean installed bolt pretension and the minimum bolt pretension, normally on the range of 1.13. Okay, so this is the minimum bolt pretension based on the table, and this is the mean or the average installed bolt pretension placed in the field. So HSC are hole size factors, which considered standard holes, oversized short slatted holes, long slatted holes transverse to the load, and the long slatted holes parallel to the load. So standard holes, of course, are simple holes like this. Oversized short holes, short slatted holes are somewhat ovalized like this, and long slatted holes are actually the form of a, okay, like this, wherein the loads are transverse, and these are simply long slatted holes wherein the loads are parallel to the load. So for NS, this is the number of slip planes, or simply the number of shear planes. Okay, so if we want to make use of the shear uh, equivalent, the shear force equivalent, we're referring here to the number of shear planes into which the bolts will be failing in shear. So for the minimum bolt tension, TB, this is again given in my lecture, but if you want to go to the AIC table, this is table J3.1. So let's understand now the calculation basic computational procedure on how to determine the tensile capacity of the connection, such as this connection shown, wherein there are 4 bolts, 2 bolts per row. We have 2 rows of bolts parallel to the tensile force. The center spacing and the edge distances are given. We assume standard size holes, and the plate is 5/8 by 6. Okay, so considering a slip critical connection with the usual clean mill scale class A surface condition, diameter of bolt is 7/8 in standard holes with A572 grade 50 plate material. We determine the design strength, which is governed, of course, by tension fracture at the connection, and that is simply this one. Okay, if you want to check for the yield, you simply compute Phi FYAG, but this will appear to be greater than this Phi FUAE. Okay, so this will be the one to be considered in your the member design. It's the capacity, required capacity of your member. So VTN is then 0.75 times 65, okay, multiplied by the effective area. There are no staggers. This is a plate, so your shear log factor is simply equivalent to 1. You don't have to worry about it. Therefore, your AE and AN are simply the same. Okay, so this is 6. The width of the plate minus 2 bolts multiplied by the diameter of 7/8 inch, we add up to the allowance of 1/8. Okay, so plus 1/8, so this becomes 1 inch diameter. Then we multiply it by the thickness of the plate, which is 5/8. So this is in parentheses. So we have now the area times the stress, for the strength is simply equivalent to 1 to 1.875. So the nominal slip resistance Rn now is computed on based on the formula mu du HSC and S, where mu is 0.35 for class A condition. So you can refer here. Okay, so this is your mu. And then du is 1.13 and HSC is 1 and NS is 1. Okay, HSC is the standard hole, and NS the number of slip planes, in which we consider only one slip plane here, okay, passing on each of the ball. So computing it, Rn now becomes 15.425, and multiplying by the reduction factor phi, which is always taken as 1 for serviceability issues. Okay, so this is now 15.425 and consider 4 bolts, we get 61.5. Of course, this is in kips, and if we compare it with the R or VTN here, this 1 to 1.875, the slip critical design connection, therefore. Okay, so this phi. Uh, okay, so what variable did he use here? So this is VTN. Okay, 1 to 1.875. 1 to 1.875. So this will govern now because this is less than. So when you say that slip critical connection are critical from the word itself. Okay, so because it's an ASD requirement, it's perhaps very much less than what the LRF requirement will give you. So relating the design strength to the service loads now, using this as your 61.7 as your TU, okay, equating it to the required strength, we get this equation, and we take note that on the problem, your live load is considered 3 times the dead load. So we compute for the dead load here and the live load there. Simply your total service load is simply the sum of these two loads here, which is 41.133 kips. So that's for the basic slip critical connection computations we have. So let's push or move forward to a more common, okay, uh, problem in design of connection. So we have here a bearing type connection, which is actually a combination of shear and tension behavior, okay. So these are normally a combination of shear and tension behavior. Although this is a shear connector because this is only connected on the web. So eccentric shear. This is an eccentric shear example. Okay, and this is a moment. Okay, connection. Okay, so this is an eccentric shear connection. And we also have a combined shear and tension connection. Okay, here it's a purely tension connection with a gasket plate here, and this is a type of a bracket connection, which is also an eccentric shear connection. So since these are although this is concentric, there is a tension involved, so it's still a shear and a tension. So all of these are combined shear and tension, but they are uh, well defined in terms of their major action. So this is eccentric shear, moment, tension, and this is again an eccentric shear. Although this is a bracket, this is a beam column connection, this is a beam to column connection, and this is a tension member to column connection. So in the earlier sections, we actually have the nominal strength of the bolts loaded separately in the shear and tension behavior, but now we will be interacting the two. We will be combining the two, the effects of the two. So when the full strength in tension is therefore required, the full strength in shear uh, is also available in this case, although in the previous discussion that's not the case. Hence, we need to have an interaction equation in this relationship. And an interaction equation for shear and tension is a circular relationship. Okay, but of course, circular relationships are difficult to solve because of the exponent. We can actually make use instead of having a circle, no? So the interaction can actually be approximated by simply putting some linear assumptions. We can make use of linear assumptions to approximate the interaction limits, no, by this trilinear. Okay, so this is a trilinear uh, limits or boundaries. Okay, so the above relationship is simplified into a straight line expression as follows. So the point 3 there is simply to add to the intercept. Okay, so if I have here a circle as my uh, okay, so if I have here an interaction equation in the form of a quadrant of a circle, so I might as well make use of a limit, a trilinear limit in the form having my intercepts, okay, higher, slightly higher. Okay, so I can have my intercept at this point and at this point, such that if I connect these lines here, I get a failure line upon interacting the two limit state condition in this form. But of course, this is a very erroneous approximation at this point, so I better have a limit here and a limit there. Okay, so these limits here are simply the 30% addition, no? So this is actually point 0.3 and point 0.3 of these boundaries exactly at the edge of the circle at that point. So that's why if I make use of this line, the 1.3 here simply defines the intercept, no, here. Okay, so we take note that the equation of line using the uh, the intercept form is simply in this format wherein x over a, okay, plus y over b is simply equal to the intercept, sorry, yes, the intercept k. Okay, so this k here, the k value here is actually the 1.3 there. And if we're going to use the ASD, of course, we get rid of the phi and substitute your omega as the basis for your uh, capacities. Okay, so Fn over omega is the capacity in ASD, while phi Fnt is the capacity for LRFD in terms of tension and shear. So multiplying the LRFD by Fnt and solving for Ft, we get this equation. Okay, so if you are going to simplify this class, mathematically, the error here is that you have to have, let's say, uh, an Ft over phi, okay. Uh, if I consider this equation here, so I will be having an F nt here plus an Fb over phi F and V there is equal to 1.3. So this is actually simplified in terms of Ft over P in this form. Okay, so we simply uh, get the value of 1.3, okay, Fnt minus Fv over Phi uh, F and V. Okay, so you will notice that here in this equation, uh, your Ft over V has no phi there. No? So there's no there's an Fnt here. Okay. Okay. So the missing F here is due to the fact, or phi rather, there's a missing phi here is due to the fact that if I convert later my value for FB, I will be using the LRFD load instead of the ASD load, because FB here is more of an ASD, allowable stress designs variable. It's not an LRFD variable. So LRFD load all over AB is FB. So to get rid of the phi value. So I'll show you that when we go to the problem, so that you won't be confused. Okay. So the tensile stress in the bolt must satisfy now this value, wherein this value is approximated in terms of another variable f prime nt. Okay, so f prime nt is simply equal to this, which is equivalent. We take note that f prime nt is simply equal to ru, or uh, phi f prime nt is ru um, all over AB. Okay, so these are stresses. Okay, RUT is the factored tension load on the bolt. Again, it's an LRFD load. Okay, so RUT is an LRFD load, although we are considering again an ASD interaction equation. So AB is a gross cross-sectional area of the bolt, and phi is the 0.75 uh, a factor for reduction uh, given in the LRFD code. So for an A325 bolt, the value of FNT over FNB is taken as 1.9 and 1.5 respectively for N bolt and X bolt. Again, N means threads included, okay, and X here means threads excluded. So note that if you use FNT is equal to 90 for A325 and 113 for A490 given on the table, the equations of phi f prime nt are simply summarized in this table below. Okay, so this 117 here was just obtained by merely multiplying the 1.9 value multiplied to the uh, value of your uh, uh, what ultimate tensile strength of your ball. Okay, so that's an FUT. Okay, so this is now 117 is one if is your value for this. Okay, phi FNT is 1.3 times the value, and then this is 1.9 of your FB here. Okay, so this is for threads excluded, and for uh, threads excluded, and for threads included. You notice that this value for threads included uh, this is the value for threads included is bigger than the value for threads excluded. Okay, because when you have the threads excluded, then your area of the bolt will be reduced. No? So if we are taking stresses, you have a bigger stress when the threads are uh, considered or included. Okay, so this is now the graph that I'm referring to a while ago, and therefore we can simply state that the point 3 of phi and b here is actually the limit upon which your interaction equation or line, this is the line, the simpler line, will cease to increase in magnitude. Okay, so this is the limit. So you have here this horizontal line as your limit for the ft value, and this is your vertical line as the limit for your shear value. This is tension, and this is the shear. Okay, for the dimensionless shear tension strength interaction equation, so we are now solving here. Remember that we have solved the f prime nt as a function of your fv here. Okay, so this is the f prime nt, or the phi f prime nt as a function of your fb. So you will yield a similar shape, but of course the values are different because it's no longer a slope or an intercept equation. Rather, this is now a simple linear equation in the form y is equal to a slope multiplied, or slope added to an intercept. Okay, so this is now your equation for A325 excluded, and this A325 included. So this is just a sample interaction, shear tension strength interaction equation. So note that the presence of the tension in a slip critical connection is reduces the clumping force. Okay, so tension reduces the clumping force. So if we have a bolt that is sheared and tensioned, then the clumping force will be reduced, simply because if you tighten the bolt, the bolt tensioning will actually be uh, counteracted upon by the tension force. Therefore, a reduction in the frictional resistance will be uh, achieved in such condition, and the available slip critical resistance now must be reduced by a reduction factor considering this Ks here, equivalent to 1 minus Tu all over du NBTB. Okay, so as an example, these parameters are still the same parameters where we use on the simple slip critical uh, okay, slip critical connections, okay, without tensile forces. So as an example again, we now have this bearing connection, the bearing type connection involving a P, which is of course concentric to the connection, to further not to further complicate matters. This is a standard T section uh, used as your connection member or connector. With this angle 345, we can therefore solve for the components of your tension force P here, which is 75 kips. We have 1, 2, 3, 4, 5, 6 bolts in total, 3 on one side of the flange, and the other side of the flange we also have 3. So consider now a bearing type connection. We solve for the X and Y component of your PU there, where PU is a combination of the dead and the live load. So 1.2 of 0.1 times 75 and 1.6 of 0.9 of 75, taking note that this is 10%, okay, of the total load, and this is 90% of the total load, uh, considering the dead and the live load respectively, as given here in this problem. So we're considering an 8325 bolts use, uh, threads excluded from the shear plane. Okay, so slip critical connection 8325SC with class A surface condition standard holes is also considered. So assuming that the strength of the column flange or the connector, the ST connector section does not govern in the design and neglect prying action, we simply determine the adequacy of the fasteners. So the prying action has something to do with since the load is inclined, there might be a consideration of having, okay, a fulcrum action, noting that at this point when you pull this, there will be what you call a tendency for this to what, to pop out, while this is not moving at this point. So there will be a change in a pretensioning, or sorry, a change in the pretensioning load of the bolt due to the uneven, or the varied tension, as uh, as can be seen if we do not neglect the prying action. So assuming that the PX here will give you a uniform distribution of tensile loads there, then we made we consider a more simpler problem, but we can actually consider the prying action later, but just to demonstrate the procedure on how to deal with a bearing type connections like this, we first neglect that prying action. Okay, so the gravity loading is 10% dead load and 90% live load. That's why there's a 0.90 and 0.1 here. Okay, so if we make use of the 3-4-5 triangle, this is simply 4/5 of PU, and this is 3/5 of PU. So the factor loads per bolt are simply this divided by the number of bolts, and this. Okay, so this is the shear VU, and this is the tension TU. So the factor load shear stress is now given by dividing, no, the VU there with the area here of the bolt. Okay, so take a look now here. I'm referring to the slip critical connection uh, FB here, or sorry, I mean the interaction equation FB. So if I consider the original equation a while ago, that this is FB over phi, and this is simply a consideration of your TN over, sorry, a TV, okay, we are on the shear, no? Or, yes, not TV. Let's use the variable here. The shear is, okay, VN. Okay, so we use VN. So since FB is an ASD variable here, so this is an ASD variable. So we use a VN over uh, a phi there. So, but Vn is simply equivalent to V over phi. Okay, so this is simply equivalent to V over phi. So we can actually ignore the phi here. So instead of having a Vn there, we simply get a Vu here. Of course, this must be divided by the AB factor there to consider. Okay, so note that your Vn or Vu is equal to phi Vn. Okay, so this will cancel out. If I use V is equal to phi Vn here, this will simply cancel out. And the Vn, the Vu will be the one to be considered in our FB equation to get uh, the shear stress, actual shear stress 19.457. And this is greater than the minimum value needed for the shear tension behavior to occur. And this is 20%. Okay, so always 20% of phi F and B. So in our interaction diagram for a beam column, normally this 20% is the basis for an interaction to be expected, or else there are some there must be some additional reduction factor to be inputted in your interaction equation to make sure that your combined effect will behave accordingly. Okay, so this is 9 KSI. Okay, and this is 19.47. Beyond the limit, so you are assured of a shear behavior in this regard. Okay, so why do we need a shear behavior? Because we are referring to the slip critical connection and not more of a tension connection uh, as your basis for the bearing type connection. So using table 14.4.1 or equation 9.9.1, so we have here this 1.3 FNT, which is equivalent to, I think this is 117, okay, if I'm not mistaken, minus, if I'm going to use, I think, what this is an 8325 volt, no? So this is a 1.3 FB. Okay, so let's look into the problem to be sure. So this is an 8325X volt. Okay, so this is an 8325. So let's look. Thread X ano. So this is 117 minus 1.5, not 1.3. Sorry. Okay, so this is 1.5. Okay, so using this direct equation or using this equation doesn't matter. Okay, it will give you the same result. Therefore, your FNT without the phi there will give you 78.068 or 086, and the phi RNT now, which is simply this one, will be 35.197 kips per volt. So the value being greater than TU, hence it is safe as the bearing type connection. But for the slip critical connection, 8325, this is again a serviceability issue. The adequacy of the slip resistance must always be checked, and the only difference between what we did a while ago is that there is a reduction factor now because of the additional the effect of the tension, which will reduce the clamping force. So if we compute now Ks in this formula, where du and b are equal to 1.13 and 6, Tb being 39. Okay, so of course your Tu here is the 15.6 we have computed a while ago here. Okay, so this is the one So we now get Ks equals 0.646. So this equation or this value is added on the original equation. Okay, so U, du, HSC are the original parameters. We are now adding another parameter reduction to account for the tension force TU. Hence, your VRN now becomes 9.965, and this value is less than the value of VU we obtained from this computation of loadings, which is 11.7. Therefore, the design is not satisfactory as a slip critical connection. Okay, so that ends my presentation on bearing type equations. I hope you have caught the general step involved in calculating or determining the adequacy of such connection, considering shear and tension as your uh, primary limit state, and adding up to the consideration of a slip critical connection in this particular problem. So thank you very much for listening. We'll proceed with the eccentric shear connection on the next video.